All right, everybody. So today we're going to be talking about mass moment of inertia for 2D problems specifically. The concept of mass moment of inertia is important in 3 dimensions in general, but I want to show you how to solve these 2-dimensional problems, so we're going to be focusing on the 2D case. In the previous video, we derived this formula, the formula you can see here on your screen. This formula is the general version of the formula for which you can sum the moments about any point, and that's equal to this term and this term, which are both due to acceleration. The left term is due to the acceleration of the center of mass, and the right term is due to the overall angular acceleration of the body. But to be able to use this equation, say for example, I give you a bunch of forces and you can calculate the moments, and I ask you what the acceleration looks like, you need to be able to determine what the center of mass moment of inertia is. What is IG? First of all, let's talk about I in general. I in general is the integral of r squared dm. If you have a general object, you must first have an origin about which everything is related to. The origin becomes the basis for this calculation. Notice that I wrote this little subscript here. This subscript means the moment of inertia about the origin. And for this integral, you take every little piece of mass in the entire object, for this example, little piece of mass dm. You take its distance to the point, r. You take that distance and you square it. You multiply that by the tiny little piece of mass. You do that for every point in the entire object, and you add them all together. For the sake of that calculation, it's important for one to consider how, sorry, I'm trying to erase this well. It's important to consider what would cause this quantity to grow. And this quantity gets bigger if the mass either gets larger or if the mass gets more spread out, either one. If the mass gets larger or more spread out, then that causes the moment of inertia to get larger. And that's important for us to consider. What causes the mass moment of inertia to get big? Okay, so this calculation is about a general point, and we don't want it specifically about any point. We want it specifically about the center of mass. This object probably has a center of mass location somewhere in here, this being point G, and therefore the distance that we're actually interested in for this dm and every other one is not the distance to some arbitrary point O, but this distance instead. I'll label that R. I think it's far more useful to label this as D than R in your mind. R is the distance here. It was a vector, but then it got squared, or rather dotted with itself, so it's just the distance squared at this point. The bigger r gets, the bigger this integral gets. The bigger m gets, the bigger the integral gets. Those are the things that cause it to have an impact. We need to consider how to take this integral. But, as I mentioned to you before, we're not going to be taking many integrals in this class. There are 2 types of problems that the textbook uses. There are problems like the one on top, here. First of all, this is a 3-dimensional problem. Not too much to say, except instead of distance from a point, like it was in this picture, it's distance from an axis. And in this problem, there's an axis as well. It's a vertical axis, one that comes out of the page at us, going through G. Just for the record. Okay, in 3 dimensions, they're going to ask you to find the moment of inertia about this horizontal x-axis. They would ask you to find Ix, which is the same principle. You're going to do the integral of r squared. Wow, I'm killing it. Integral of r squared dm, where r is now the distance from the axis to the mass. From some point, okay, I cannot draw these things without it freaking out. I'm trying to avoid it. Had this all working earlier, but I'm not sure what changed. From the axis, well, I can highlight. From the axis to the mass. So the important thing is it's in 3D, it's still the same principle, and for a problem like this, with some sort of general shape, you would have to perform an integral. This integral in general is 3-dimensional. This one. You're integrating over the mass, and the mass exists in three-dimensional space, so you have to integrate over space, and I don't want you to do any three-dimensional integrals. This integral can be simplified to 1D, but I don't really want to cover that either. So instead, we're going to be focusing on problems like the one below. Let's get rid of all this. For this problem, we approach it differently. Here's the reason. This problem is made up of some regular shapes. They're cylindrical rods. They are slender in shape, much longer than they are around. And if you perform the integral to find out what the moment of inertia is of either of these shapes, this rod here, this rod here, or this rod here, either one, you'll get a general formula that you can use for every slender rod. So we can just use that formula instead. I'll just go ahead and tell you the moment of inertia of a rod like this. Let's say you've got a rod. Okay, did my best. And you want the moment of inertia of this object. It has a length, what I'll call L. It has a mass m. The moment of inertia is equal to 1/12 ml squared. But this is incomplete because moments of inertia require you to say which point is this measured about. These formulas that I'm going to give you are overwhelmingly about the center of mass of the object, the middle. And for these irregular shapes, the centroid is easy to predict. I know where the centroid is. It's a symmetric rod, so it's in the middle. This formula is the formula for the moment of inertia of a slender rod about its center of mass. In the picture for the horizontal rod, that would be right about there. It's a 1.2 meter long rod, so it's going to be 0.6 meters over. I'm going to call this G2. And then the vertical rod here has a height of 0.4 meters and a center of mass right in its center. I'm going to call this G1. And this formula, the one I've given you here, gives the moment of inertia of these two shapes about their center of mass. So I'll go ahead and label these shapes. I'm going to erase all this stuff. Remember, the moment of inertia of a slender rod for a slender rod the moment of inertia about its center of mass is equal to 1/12 mass times length squared. So for rod 1, that's this one here. The moment of inertia about G1 is equal to 1/12 times the mass, which is 1 kilogram, times the length, which is 0.4 meters squared, which, don't I wish I had a calculator here. You know, this thing's got to have a calculator on it. Let's just take a moment while I search for one. All right, I'm back, and I have a calculator now. I'm just going to plug this quantity into my calculator that I've got here. This is 0.0133. I guess I'll stop there. This is kilograms. Good try. This is kilograms meters squared. And I could do for rod 2, that's fine. Ig2 equals 1/12 times its mass, which I'll go ahead and say this is 3 kilograms, times times 1.2 meters squared, which is equal to 0.36 kilogram meters squared. I should say that for this problem, the masses would be given to you. They would give you the mass of the individual rods separately, or they would give you like a density. They would tell you, for example, in this case, the rods have a mass of, gosh, what would this be? It'd be 1 per meter, wouldn't it? No, not at all. Well, 1 kilogram per 0.4 meters. So I guess I could figure that out. 10 fourths, so 2.5. 2.5 kilograms per meter is the density on this thing. Anyway, doesn't matter. The important thing is that the masses would somehow be given to you or calculatable. I forgot to mention where these mass numbers came from. As it turns out, I just made these numbers up when I was calculating the problem a little bit earlier. I actually, for the record, went through this entire video and then found an error and decided to re-record it. So here we are. Okay. Anyway, let's focus on the issue at hand. We've calculated the moment of inertia for rod 1 about its center of mass, and the moment of inertia of rod 2 about its center of mass. But for the sake of this formula, I don't want either of those things. I want the moment of inertia of the overall shape about the overall center of mass. This is a combined object of two rods, and I need to know what the center of mass is of the shape about its center of mass. I have two problems. One, these these moments of inertia that I've calculated are perfectly nice and helpful and useful and all that, but they're not about the center of mass of the overall object. So that's a problem. We need to find the moment of inertia about the overall center of mass. To do that, we have two pieces, two things we need to consider. So I'm going to put those on this page. Thing one to consider, we need to be able to find the overall center of mass. I'm going to focus on that here on this page. Find the overall center of mass. You might recall that the overall center of mass is equal, I'll say RG, is equal to the integral of R dm divided by the overall mass. I don't want the fact that this is a vector to throw you off too much. You know, a vector equation is just all three component equations done at the same time, or in the 2D case, two component equations at once. So we could write this instead that xg equals integral of x dm divided by the integral dm, and also y of the center of mass is equal to the integral of y dm divided by the integral of dm. These two equations are the same as this one equation. They're the same. So I need to perform this integral for the overall shape. That's what I need. The bottom's easy. The bottom is just the total mass. The 0.4 meter rod has a mass of 1 kilogram, and this one has a mass of 3 kilograms. So we know the total mass is 4 kilograms. The bottom's not hard. The top is hard. Okay? So, but what I have told you before is that this integral is equal to the center of mass times the overall mass. That's not very helpful. And the reason it's not very helpful is that I don't know the overall center of mass. Like, I don't know where that is. That's convenient if true. Well, let me write this down below. M times x bar is equal to integral of x dm. In fact, this is the entire point of the center of mass in the first place. This location is where you could put all of the mass and multiply them together, and you get the same value as you get for this integral. That's the point. But there's something to recognize here. This integral can be broken up. Let me try and write this a little bit better. Can be broken into pieces. So what I mean to say is that you can integrate this over different regions for your shape, and those can individually be the x bar of the first region times the mass of the first region plus x bar of the second region times the mass of the second region plus, dot, dot, dot for all the others. So I should probably put a plus dot, dot, dot for this one too. So you can do it this way, and this is perfect for this shape, because take a look at the top shape, while for this overall shape, I don't know where its center of mass is, I can break it into pieces where I know what the center of mass looks like. That's what I'm going to do. So for my shape, the x bar location, which is the integral of x dm divided by the total mass, is equal to. Okay, so first of all, take a look at the shape, pick an origin. You can pick any point, doesn't matter. I'm gonna measure everything from here. And the reason is, that way I'm dealing with positive numbers exclusively. So, for the first shape, I'll call this region 1 and region 2. What is that? What is x bar of region 1? What is the x coordinate measured, again, from here for region 1? Well, 0. X equals 0. 0 times the mass, which as I said before was 1 kilogram, plus, okay, what is the centroid location of region 2? Well, this is a 1.2 meter long bar, so its centroid is just to the left. I am trying to make this work. Just, you know, it's impossible. I can't do it. Let's do this. I'm going to put a little box over this, and this box is going to let me write in this region specifically. So I'm going to type down in the box that you see on the bottom of the screen. It will modify the top image, but at least I won't keep selecting the image. The second rod has a center of mass here. The overall length is 1.2 meters, so the distance between here and here is, what did I say? 0.6 meters. That is the overall length. So that is x bar for the second object. So I'm going to add 0.6 meters times, what did we say the mass was? 3 kilograms of that object. 3 kilograms, again, divided by the total mass. Should really erase some of these circles I've drawn. But anyway, the total mass is 4 kilograms. If I go ahead and calculate that out, I get 0.45 meters. That means that the actual center of mass of this overall object is 0.45 meters over. I'm going to go ahead and label that on this image again. Put it right about here. This is the overall center of mass. I will label it with the center of mass symbol. I'm going to go ahead and erase this 2 and put that elsewhere. And this distance is 0.45 meters from the left. You might be wondering, could I have used O for the origin, or rather even, do I need to use O for the origin? For the center of mass calculation, you do not. For the center of mass calculation, you can pick any origin you want to. I will almost always pick the point in the bottom left corner so that nothing is negative. I didn't go to the bottom left here because I recognized in the y direction, everything's in the center. I already know where the centroid location is in the y direction. I even drew it on the picture already. I'm not super interested in the y direction in this problem, but I could be. And if I was, oh my goodness, I'm just ruining my image. Okay, let's go back. Oh no. I have a redo button? Okay, well, I've ruined it. Let's see, just draw this arrow. Okay, back to normal. Okay. In the y direction, we have the same thing, but the y direction is not very interesting. Integral of y dm divided by the integral dm is equal to, just break it up, y bar times m for each region. So y bar of the first region is 0. The mass is 1 kilogram. And y bar for the second region is also 0. Times the mass 3 kilograms divided by 4 kilograms. You do the math, it's equal to 0. The y bar location is not up or down. So I would say that we were able to find the center of mass. The takeaways here, if I had to summarize this, to find the center of mass, you must break the piece into shapes that you know what the center of mass is, and then perform this calculation here. I'm going to go ahead and erase that and rewrite it because it's gotten quite messy. I want to re-emphasize this point. The center of mass location is equal to the integral of x dm divided by the integral dm. How do you perform the integral in the numerator? Break it into regions. and multiply it, perform the integral of the regions by just replacing it as x bar of the region times mass of the region. That's the entire point, and that's what we did here. I will be doing more example problems on this. They'll be more focused just on example, as if I've already covered the material and we're just doing example problems. And so look for future videos for that. Okay, we're done here. We found the overall center of mass. Remember what we're doing though. I want to find the overall moment of inertia, not the overall center of mass. I was claiming that in this formula, this is the moment of inertia about the overall center of mass, so we need to know where the overall center of mass is. And that's great. We did that just now. If we go back to this page though, you might recall that I was able to find the moment of inertia of the individual rods 1 and 2, about their center of mass, but I don't want them there. So we have one issue left. Issue 2 is find the moment of inertia of common shapes. That A got away from me a little bit, didn't it? Common shapes about points other than the center of mass. I'm going to abbreviate that COM. So for example, if I give you a rod and I tell you that about its center of mass, I'll call this G1, is equal to 1/12 mass times length squared, where this rod has a mass m and its overall length is L. And you don't want to know it there, you want to know it, I don't know, about this point instead. I'll call this point G. Then it is true that the moment of inertia, about this other point is equal to the moment of inertia about its own center of mass plus the mass of the object times the distance between the 2 points squared. That distance is d, the distance between the 2 points. This d represents the distance between here and here. Distance between. Super important. There's a couple things that are really important. For this formula, IG1 in the above formula must be the moment of inertia about the object's own centroid. Well, object's own center of mass, I'll say. COM. This formula doesn't work in general just to relate 2 points to each other. To relate 2 points to each other, it's more complicated than this. To relate the center of mass of the individual shape to some other point, this is the formula. And you have to use it that way. The important thing to realize is that for our problems, generally this is just given. This is given by a formula. Yes, somebody had to derive that formula using integrals at some point, but it's done, so we may as well use it. This is the moment of inertia about any other point you want. I've written it as G, and the reason is that we are going to be using it for this. Because we're using it for that, we are interested in the moment of inertia of G. How does G and G1 differ from each other? This is a point of confusion, okay? So G is the moment of inertia of G is the center of mass of the overall object. G1 is the moment of inertia of the individual shape, which you are calculating the moment of inertia of using this formula, or a different formula for a different type of shape. So this means we can find, using this formula, the moment of inertia of a shape about some other point. You probably know this formula. Ig equals Ig1 plus m1d squared. This is called the parallel axis theorem. The idea behind this formula is the same no matter which version of it you have written down. And my version might look a little bit different. I'm trying to get the idea to you, though. This moment of inertia is about the center of mass of the individual piece. This moment of inertia is about some other point. This mass is the mass of the individual piece. And this distance is the distance between the 2 points. That must be understood by you, or I guarantee you will misuse this formula. I want to go back to this, where we were calculating the moment of inertia of the 2 rods. And now I'm going to do it about the overall center of mass, which is located here, 0.45 meters from the left. I'm going to do it by using these formulas, which are the moments of inertia about the individual pieces' center of mass, and this formula, which tells me how to adjust it to find it about the overall point. So let's do it. The moment of inertia of shape 1 is equal to the moment of inertia about its center of mass, 1/12 times 1 kilogram times its length, which is 0.4 meters squared, plus the mass times the distance between its center of mass. I really wish I wouldn't do that. Back to this, I guess. The distance between its center of mass and the overall center of mass. And that distance, as we recorded earlier, is 0.45 meters. So, 0.45 meters. That's equal to, well, something. I2, the moment of inertia of shape 2 about the center of mass, is equal to the moment of its moment of inertia about its own center of mass, which is 1/12 times 3 times 0, no, not 0, that's a 1.2 meter long rod, plus its mass times its distance from its center of mass to the overall center of mass. Remember, it's 1.2 meters long, so its center of mass is equal to 0.6 meters away. So what's the distance between here and here? 0.15 meters. So back to our formula. 0.15 meters squared equals something. The overall moment of inertia about the center of mass is equal to I1 plus I2, which is equal to. I'll throw that all into my calculator, because why not? Just to see if I can. 1 divided by 12 times 1 times 0.4 squared plus 1 times 0.45. Oops, got to square that. There's an error in my first formula. Let me bring your attention to it. The first formula, this one, the distance is always squared. Okay? So let me get rid. Let me get rid of that. Put the squared back on. Okay. So 1/12 times 1 times 0.4 squared plus 1 times 0.45 squared plus 1/12 times 3 times 1.2 squared plus 3 times 0.15 squared is equal to 0.6433 kilogram meters squared. This value must be used if we are going to find the angular acceleration of this object if it was released from rest. We can do that problem now, but I'm not going to. Cool. Maybe we'll look at that in a future example problem. That's it for this video. The overall principles are about calculating moment of inertia, about the center of mass of a composite shape. That is a shape made up of multiple pieces. Many of the problems in this chapter don't have multiple pieces. It's just a single piece. So it's much simpler than this. You don't have to struggle to find the center of mass. You don't have to struggle to use the parallel axis theorem. You just use the formulas that are given. But if you do have a composite shape, you must do all of this, just so we can get this number. Once we have that number, the rest of the problem proceeds. All right. Look for other example problems. I'll be posting stuff to Canvas regularly. These two are what we need at first, and I'll be doing examples in the future. So I hope that this was comprehensible. Feel free to ask questions via Zoom or office hours. I will see you all later.